Hello class, welcome back. We are still on chapter 4, diodes, and this recording is the remainder of chapter 4, um, and that includes the sections on rectifier circuits, 4.5 in the chapter, and there are two more sections after 4.5. One of them is a collection of circuits such as the limiter circuits and voltage doublers and so on. So that's a short section, and then at the very end there is one slide I have on some other special purpose diodes, but we'll cover that also rather quickly without going into too much detail. So most of what I want to cover in this recording is the theory behind rectifier circuits. The next recording will be to look at problems, mostly on rectifiers, and with that we actually finish this chapter 4, diodes, and move on to the next chapter in the next recordings. Okay, so that's the plan. Let me start with this slide, which is slide 29. Okay, and we are looking at section 4.5 in the chapter. Okay, so rectifier circuits are probably not something too new to most of you. I'm sure somewhere or the other you've been exposed to a little bit at least of rectifiers. I remember even in our last class, 188, we had the opportunity to look at some diode circuits very briefly. This may not be new, but certainly I think we'll be doing a lot more detailed study of rectifiers than anything you've done in the past. So let's start off with this nice block diagram of rectifier, and this is in our textbook. I don't know what exactly the figure number is, but you will find it in section 4.5 right at the top. So let's look at each of the blocks in this block diagram so that we have a better understanding of what rectifiers are. So first and foremost, you need a power transformer, because generally if you're going to supply DC power, now obviously you know what a rectifier is. It converts AC into DC. That's one simple way of looking at rectifiers. And I know we were briefly introduced to this even in the first section of this chapter, 4.1, where I think briefly introduced you to a half-wave rectifier. But the bottom line is a rectifier works off of an AC circuit or an AC supply and converts it into DC. So generally DC requirement is at a much lower voltage level than AC. AC, even if you assume the lowest level of AC available is what you get in our residential connections, that means in our homes, from the outlet on the wall, those can be 120 volts or 220 volts, right, 230 volts. So that is the lowest generally easily available AC. Even that is pretty high. AC devices such as your, the refrigerator in your house or the washing machine, those can work directly off of these 120 or 220 volt lines. But a lot of electronic devices, including your cell phones and televisions, etc., those need lower voltages, because electronics generally tends to be 15 volts or 5 volts DC, generally in that range. It doesn't go up to hundreds of volts like AC devices. So the first thing you need to do generally in a power supply is to step down the voltage of an AC source. So that's why you have that power transformer on the very left side of the drawing. And then once you step it down to somewhat closer to 30-40 volts, that's when you introduce the diode rectifier section. The diode rectifier section can come in a variety of forms, and that's what we look at in the rest of this recording, where we talk about half-wave rectifiers, full-wave rectifiers, and so on. So the diode rectifier section generally doesn't give you a smooth DC. Now the goal is to get, when we say DC, we assume one constant line, right? That's the best type of DC. Normal rectifiers put out a pulsating DC. They are DC, they are on one side of the axis, they never go down to the negatives, but they don't, they're not one line, a solid straight line type DC. They tend to be like half AC waveforms, right? So you need to filter it, and filtering gives us a much improved DC. It's still not perfect, it still has some ripple, but it's still a lot better than what comes out only from the diode rectifier stage. Okay, so after, and you can see from these nice waveforms in blue in the picture what the shape of each one of these output of these blocks are. So even outside the filter, or out of the filter, you have that rippling DC. Then you enter the voltage regulator section, where you actually get a very solid straight line with almost no ripple at all. So if you put all these sections together, then you get almost a perfect DC that you see at the very end, and your load is pretty happy, because most electronic loads want that kind of straight DC, straight line DC. Okay, so anyway, these are the various sections. We don't go into too much detail. I mean, designing rectifier circuits and power supplies is a full-time job for a lot of engineers. So we'll be introduced to many of these concepts. In fact, the voltage regulator, you already learned a little about it last time. You string 3 diodes together and you get a pretty nice DC voltage regulator. Transformers we studied in the last class, so you have some idea what a step-down transformer is. Turns ratio, it works off of the principle of mutual inductance, so I'm sure you're somewhat familiar with all that. But of course, in this section we'll focus a little more. Filters also, you know that an RC circuit can be a good filter, or an RL circuit can be a good filter. So the section that we are most concerned with in the next 20 minutes is going to be diode rectifiers. Okay, so let's move on with that introduction from slide 29 to slide 30. So now we are at slide 30, and we start by looking at something called a half-wave rectifier. So in the simplest form, a half-wave rectifier, as you can see from the circuit diagram to the top right, has one diode, and it's connected straight to an AC source. Now the AC source Vs that is shown there, I show it as Vs equals capital Vs times cos phi. It can be the secondary of a transformer, or it can be directly off of a transformer, which means the diode has to be pretty large if it's working directly off of 120 volts, but generally you have a step-down transformer. So in any case, there is an AC source that then is tied to a diode, and then of course you have the R, which represents the load, and then you have an output voltage. So if you look at the transfer function or the input-output diagram, which is just below the circuit diagram, you see how the input and output are related. They're pretty much related by a factor of 1. That means V out equals V in, or Vs in this case. But it's not, and then that's true for most of the positive region and 0 for the negative region, because the diode, we know, only conducts in the positive cycle, because in the negative cycle of the AC waveform the diode is reverse biased, and so it doesn't turn on. The forward direction it turns on. And we also know that unless it's an ideal diode, which is not real, an ideal diode we assume just turns on at 0 positive, but a real diode, it has a cut-in voltage, a delayed voltage of about 0.6 or 0.7 or 0.8, and that is that VD that you see on the graph on the right side. So after the voltage, the AC voltage in that positive half cycle rises to greater than VD, which is about 0.7, then the diode fully conducts, and really everything on the AC side comes to the output side, because there is no other resistance or nothing else to drop the voltage. So as you can tell, the slope of that line connecting the input and the output is 1, meaning V out equals V in after Vd. So if you look at the AC waveform below the last figure, you'll see the blue part of the waveform is the output voltage. That is the voltage that appears across the resistance, and the black parts of the waveform are all just the input waveform, which is a pure AC waveform. So you'll notice that there is a delay, and that delay is Vd, and after Vd is reached is when the AC starts, the diode starts conducting. Okay, so the waveform for the output is somewhat distorted. It is not exactly a replica of the positive cycles of the input AC. Even it is kind of smaller by the factor Vd, and it's also has a shorter on time than than just half of the cycle, right? With ideal diode you can assume that it's the complete half of the cycle of the input AC, but a real diode is actually shortened even when it comes to the on time. So you can see all these factors from the figure give some thought to all those details shown in the graphic, because it's easier for you to just look and observe what is happening there than for me to try to explain it to you. Other factors that we must pay attention to on this slide include the maximum diode current, which is shown there as Vs minus Vd by R. The total conduction angle, I think we already did a problem related to this, but the total conduction angle is another important factor when it comes to particularly to solving problems. Some of these are derived in the chapter, so please look at the text to find a little more detail if you're interested. And then we have a couple other important things. The average or DC value of the output, there's a formula for that. And lastly, there's something called peak inverse voltage, which is an important parameter. So when you specify a diode, you have to at least say two things. First, what current do you expect the diode to handle? And so the larger the amount of current it needs to handle, the size of the PN junction and the size of the diode tends to be larger. The other factor is what is the reverse voltage that it may face, right? So you can't take a little diode that you use in the lab to normally handle 5 volts DC. Maybe it can handle about 20 volts of AC reverse across it, but after that it can break down and or cause other kinds of operation. So the peak inverse voltage is a measure of how much strength it has to oppose reverse biasing. As the AC negative cycle is fully applied to the diode, it has to withstand it, and it has to prevent the breakdown and current to be conducted, and that measure of that is called peak inverse voltage. Okay. So we'll study a little more about all these, but this was your first introduction to some of these, terminology. VO is generally V output, Vs is generally V input, but it's also shown as Vs or Vp as peak sometimes. Vd is generally the diode voltage. That means the diode on voltage. So when the diode begins to conduct, its natural voltage across it is roughly constant, although we know it's not exactly constant. It sort of depends on the value of the current, but roughly speaking, we think Vd is a constant of about 0.7 or 0.6 volts. Okay, I'm going to skip to the next slide, to slide 31, and here we introduce a filter capacitor with the hope that the output of the filter capacitor is somewhat more like real DC that we are used to than that pulsating half sine wave that we saw on the previous slide. So with the filter capacitor, now lots of interesting things happen. So as you can tell from the, let's look at the circuit diagrams. On the left, you just see one filter across the diode, and underneath it you see that the waveform now has become totally different. Previously it used to be two half waves, half AC sine waves, or a positive and then a blocked negative and then a positive. But here with the capacitor, it's almost like a steady output voltage V0 after the capacitor first charges in the first quarter of the first half cycle, and then nothing else at all. It just seems to stay constant. I mean, it's not really constant, it's slightly tapering down, but it's almost constant. Then now having a circuit like that is no use, right? Because generally you need to apply a load to a circuit like that. So it's unavoidable that a resistor shows up, which is what you see in the next circuit drawing, where a resistor is now connected in parallel to represent the load. Now we are talking more like the real world, right? And for this system or this circuit, the drawing on the right side, the AC waveforms, now are much different. And what you see here is the blue waveform of the output, which is pretty close to DC, but not quite a stable DC, a steady DC. It seems to charge up in a part of the AC, the positive cycle, and then it slowly declines, and then it gets charged up, or boosts, and then it declines, and so on. So you see how the capacitor goes through a charging cycle and then a discharging cycle when the AC waveform is on the falling trend. So when the AC waveform is rising, at a certain point it starts to charge the capacitor, and then when it starts to fall, the capacitor now starts to discharge into the load. So if the capacitor is a large enough capacitor, it doesn't discharge too much in any given cycle. It starts to discharges a little, but then it catches the rising waveform again. So how much does it discharge is shown by that VR that I circled in red, and that voltage peak to peak is called the ripple voltage, or VR. Okay, and VR is a very important factor when it comes to analyzing filter circuits, well, rectifier circuits. So pay some attention to understanding VR, why it happens and why it exists, and in the next slide we'll deal with it. But just a couple more things I want to point out. If you look at the bottom portion of the waveform of the graph, you'll notice that there are two pulses, almost pulses, and they're shown to be on only for a certain amount of time called delta t. So the conduction interval in this case, compared to the previous case where the diode would be on for a long time, in this case the diode actually needs to be on for a very little time, because the capacitor takes on much of the work of actually delivering voltage to the load. So the conduction interval, or the on time of the diode, becomes much smaller, and you see how it pulses. But that doesn't mean the load is not getting the current. The load is getting the current, and the IL in blue is the load current, and you will notice that that tends to be fully, almost completely, there is load current. Okay, the diode current is a much smaller pulse as shown. Okay, so I hope that is clear. Then a couple of formulas in the middle there which are important, again from a point of solving problems. The V output is shown to be V peak minus Vd minus Vr by 2. So Vp, remember I said the input voltage is generally shown either with a Vs or a Vp. In fact, in this case it's shown as a Vi. Now Vi is a sinusoid. It has a maximum value of Vp and then cos theta or cos phi. So V peak is shown to be the highest possible value of the AC waveform, the input AC waveform. So the output voltage Vo, if you consider it also to be a bit of a time function. I mean, the goal is to make it flat so it is not a function of time, but in reality it's a little bit pulsating, so it is a function of time. And what is its value at any given time? It's Vo equals Vp, and then you have to subtract the diode voltage Vd, it's about 0.7, and then you take half the ripple voltage. So the ripple voltage is this full value, right, from there to there. And generally ripple voltage is given as a value like 2 volts maybe, or it's also given as plus or minus 1 volt. So plus or minus 1 volt going above and below a certain center line can also be considered 2 volts. So it's given either way, so be careful which one is given. But if you think of V ripple as this full value, that value, then in the formula you use Vr by 2. Sometimes we can just ignore that Vr, because compared to the Vp, let's say Vp is 20 volts and Vr is maybe 1 volt. Then compared to 20, Vr is pretty small, right? Then you can ignore it. Now on the other hand, if Vp is only 5 volts and you have a ripple of 1 volt, then that's a 20% ripple. So depending on how big the ripple is or how small it is compared to the Vp, you can use either formula. So that's why I put this approximately equal to. Okay. So I have to move on. I hope this slide was useful in pointing out a lot of concepts related to rectifiers, and we will use these same concepts a lot, so become familiar with them. Next slide, also still on the same topic of half-wave rectifier with filter capacitor, and here I'm defining the ripple. so maybe it will help you to understand it better. But a ripple is the residual periodic variation of the DC voltage within a power supply which has been derived from an alternating current source. So generally, if you have a battery giving you a DC power, there's no ripple. You don't think of a ripple in that situation. A ripple only exists if you're getting your DC through a rectifier from an AC supply that's feeding the rectifier. Okay, so that's what this definition says. So ripple voltage, there's some formulas for exactly what the ripple voltage is, and these are again all derived in the chapter, so please pay some attention. But you'll notice that the ripple depends on R, C and F, all these factors that we are familiar with, the resistance, the capacitance, the frequency, and also Vp, which is that peak voltage. So sometimes that Vp is written with a Vp minus Vd, the diode voltage. Sometimes the diode voltage is dropped if it's not if it's small in comparison to the Vp. But either case, you must be comfortable with the concept that the ripple voltage depends on all these factors, and there is a formula to use when we are solving problems. Similarly, the conduction interval has a formula, so sometimes you may have to use that. It depends on the ripple, the ratio of the ripple and the peak. Then there's also something called the max reverse voltage, which is VO plus Vp in this case. The max reverse voltage is kind of like the peak inverse voltage, right? I talked about the peak inverse voltage already, but sometimes you first derive a max reverse voltage, that is the voltage that the diode sees, and then you apply a safety factor, generally about 1.5, and then you say, okay, the PIV, peak inverse voltage for the diode, is so and so. So if the max reverse voltage, let's say, is 20 and you apply a safety factor of 1.5, then 1.5 times 20 is 30, so then you say the PIV is 30. Okay, so we'll do some problems and you'll become more exposed to that. Last thing you see at the bottom there on the left side, slide 32 again, is the IDAV. So the diode current. Now the I load current is here. Maybe I didn't show it to you specifically, but the load current IL is obviously the output current VO divided by the resistance, right? The applied voltage divided by the resistance. In fact, that formula is used somewhere here also to solve for the output current, IL. Similarly, we have the diode average and maximum diode current. These are used, these are important, and they show up a lot in problems. But here's a formula for it. The diode average current is the load current times something. Similarly, the max current is also the load current times something. Generally, as a general rule, you can say that the maximum is twice the average. Okay. What else can I show you? These diagrams on the right, they're just a copy of what we've already seen. So that's about everything on this slide, which is about a half-wave rectifier with a filter capacitor. Okay. So I have an example that we will hold off until we get to the next recording. Okay. So I moved on to slide 34, where we now start looking at full wave rectifiers. So far what we have done is look at a half wave rectifier with only one diode. Now, if you are able to afford to buy two diodes and you can suitably modify your transformer, then you can actually come up with some very good rectifiers which can handle higher currents, which can put less stress on the diode, so you can buy some cheaper diodes, and the ripple also comes out to be somewhat more better. You don't eliminate the ripple entirely, but they are somewhat lower than in the case of the half wave rectifier. So we are going to study full wave rectifiers, two versions. One, what's called rectifier with a center trap transformer, and the other, a rectifier with a diode bridge. So we'll study these, and then also I will tell you we do bring a filter capacitor back, and then we study, the theory of full wave rectifiers with filter capacitors. Okay, so that's what's on the cards for the next few slides. So let's look at the two types of rectifiers, and try to understand how exactly they work. So in the circuit on the left, what you see is a transformer with a tap in the middle. So what that means is, from one transformer you're actually getting two different secondary voltages. Remember, transformers have the primary voltage and the secondary voltage, right? The secondary voltage, you're kind of splitting it into two, and so in an arrangement like this you actually get two full AC waveforms from from the two halves of the secondary. So the first full AC waveform is applied to D1 and the second is applied to D2. So D1 only works for half a cycle, right? The other half, it just blocks the half cycle. But while it is blocking the second half, the D2 picks up that second half and it is now conducting. Okay, so the two diodes work on one half each of the halves of the output of the transformer, and so they give you something that is like this blue output voltage, right, which you can see is conducting in both half cycles of the AC waveform, of the input AC waveform. So because you have two diodes, the duty on any one diode is kind of reduced, okay, compared to the previous case where you only had one diode. The load is still just one resistor, and the nice thing is, remember, we have not introduced filters yet, so the load resistor sees this nice blue waveform applied to it. The blue waveform has two pulses representing the two halves of the AC waveform. So it's better than if you only had one pulse and then a long gap for the remaining half of the AC waveform. So the two pulses gives it a better average value of DC. The same thing is also achieved using a bridge arrangement of 4 diodes. In this case we have 2 diodes, in this case on the right side we have 4 diodes. And what does the 4 diodes do? They work in pairs. And I think we already studied this when we did the 4 LED lab. I think you saw the 2 LEDs light up in pairs. So I think you're familiar with it, but if you want to trace what happens when this line is positive, this D1 conducts and D2 conducts. So D1, the current flows through D1, through the load, out of D2 and then back. And the opposite happens when this is positive. So when the lower terminal is positive, D3 conducts, the current goes through R, then D4 conducts and it comes out. Okay, so that's the simplest way to understand it. Now what you'll notice is that there are differences even between the two. They are not identical. In this case, on the left side with just the center tap, the gap between the peak and the peak of the incoming and the peak of the DC of the load voltage is Vd, while here the gap is twice Vd. So if the Vd is 0.7, in this case you're actually getting a lower value out of the bridge in terms of the peaks. Okay, so just something you need to know. Yeah, everything else is pretty simple. The blue is the output, so that's about the extent of the information on this slide. Okay, so I'm going to move to slide 35, and here I give you a summary of some important relationships amongst the voltages and the currents, both on the on the load side and the input side. And we still haven't introduced a filter capacitor. So normally we generally, for solving problems, we end up in situation with a filter, but still remember these values, at least get an idea for them because they can be useful. So what are the two sets of values telling us? Let's start at the top. So the rectifier with the center tap transformer, top left, the output voltage has this simple form where you start with the input peak, the Vs, then you subtract the Vd, and then you do the Vr by 2. So in this case it seems similar to what we did with the half-wave rectifier. But once you come to the right side, the rectifier with the diode bridge, the Vd now becomes 2 Vd, which you saw also in the previous graph actually. So there are some differences, and when we solve problems we have to remember to use the right formulas. The maximum diode current in this case is Vs minus Vd by R. Here it's Vs minus 2 Vd by R. The total conduction angle also slight differences. Average or DC value of the output voltage, or they're slightly different. And then maximum reverse voltage also has this form on the left side and has this form on the right side. So there are slight differences, and be aware of those. Are there any big differences, big advantages or disadvantages between the two? Well, here's a couple. Obviously the second one requires only 2 diodes versus 4 diodes here. That is one difference. The transformer needs a center tap on the left side, while on the right side you don't need a center tap and you only need half as many secondary turns. So which is cheaper depends on so many things, but generally speaking the bridge configuration with 4 diodes is the most commonly used, but there's no hard and fast rule. It depends on which makes most sense. Remember, rectifiers can be very small, like we use in the electronics lab. Sometimes they can be very large for high power applications. For example, in the production of aluminum, for example, you have an electrolytic process that needs maybe 1,000 amps DC. And in such processes where you need very high amperage DC currents to run huge factories, you may be better off using, because diodes can be very expensive there, the transformers can be cheaper, and so the bridges tend to be half wave or even full wave with center tap in those cases. Okay, so that's some general information. I'm going to move on. I know, as always, we seem to be short on time. Now we look at the configuration of a full wave rectifier with a filter. Okay, with a filter the waveform seems a lot more comforting. You don't have those pulses and the output voltage is starting to look more like DC. So I show you just one example of having a bridge and so that we can use this to summarize all of the relationships. Many of these are derived in the textbook, so please read if you are interested. And it also helps to understand the theory more about what is happening and the diode currents and the diode voltages and the load currents and so on. But for purposes of time and to keep moving, I generally give you a summary. So what does the summary say here? With the filter capacitor, the output is still pretty much the same. It's Vp minus 2Vd minus Vr by 2. But the relationship that defines the ripple, we've already seen this for the half wave case. Even for the full wave, the ripple voltage depends on the frequency, the capacitance, and the load. Okay. Again, sometimes we bring in the 2Vd into the formula, sometimes we don't. It depends on how big or how small the Vd is compared to the Vp. So remember the relationship for the V ripple. It's an important relationship. We use that quite a lot in problems. Then there's also the formula for the average current in the diode and the max current. And of course the load current also, you will need to be familiar with that. The load current is the output voltage divided by the RL, the load resistance. One important interesting fact here at the bottom, for the same values of Vp, Fr and V ripple, and that's the same I load, the capacitor value is only half the size of that required in the case of the full wave rectifier. So the current also in each diode becomes half. So the nice thing is, having a full wave rectifier compared to the half wave helps with reducing the size and the cost of the capacitor. And this is a very important relationship to be aware of, because capacitors can be quite expensive. And some capacitors, we generally deal with capacitors in the microfarads, but once you start getting into the millifarads and so on, larger capacitors can be expensive. So it may be cheaper to create a bridge with 4 resistor diodes and make a full wave bridge instead of a half wave with just one diode. So there's a trade-off in cost. Okay, so you should be aware of that. The diagrams, there's not much to show. I found this diagram somewhere else. It just shows you much better what the shape of the output, the rippled output will be on a full wave bridge. Okay. All right. So I'm ready to move on. Next is a problem, so we can wait to do that later. Another problem, we'll do that later. Actually, 2 problems, we'll do that later. There was actually an example somewhere. Did I miss that? Oh, there's an example also on slide 33. So we'll do all these in the next recording. So let me move ahead and see what else we have. Yeah, so that was pretty much it for rectifiers. So we studied the full wave rectifier, the half wave and the full wave. We looked at the center tap full wave. We looked at the bridge full wave. Then we looked at those rectifiers with capacitors and how the capacitors. Now, without the capacitor, the ripple is significantly high, right? The ripple is almost equal to the output voltage is all rippled. But with filters, the output voltage has a small ripple, and so it's still there. So we need to know. In fact, just studying the ripple can be a whole week of analysis, because the ripple has it's an AC waveform. It has some harmonics, and you can design much better filters. All we looked at was one capacitor. You can actually create a full RC filter or 2 capacitors, 1 resistor, capacitor, inductance, all of these. So filter design for reduction of ripple is itself a big subject. We're not doing too much of that here. We're just using one capacitor to understand the reducing the ripple idea. but it's an interesting topic that maybe sometime in the future you'll study. Anyway, that ends the filter, the rectifier business. So the next few minutes I'm just going to look at these circuits. Uh, there's a collection of circuits all that use diodes. They're pretty interesting, but we are not doing them in too much detail. I just wanted to introduce them to you. Limiter or clipper circuits, that's the one on the top, and I'm on slide 39 by the way. So the limiter or clipper circuits, what do they do? So if you look at this nice diagram on the graph, the plot on the right, what you see is an AC input coming in and the output is clipped. Both on the positive half cycle and the negative half cycle, the circuit chops off the top portion. So that property is called clipping or limiting, and it is useful for a number of applications. Okay. The next, and see how these diodes are connected in a rather interesting way. There's two back-to-back diodes, right? You might think, what good is that? But hey, now you can see what good it is. It helps to change the wave shape, the shape of the AC waveform. Clamped capacitor or DC restorer. So what this means is you're able to actually take input waveform that has like +5 on the top and -6 on the bottom and shift the whole thing up so that you get a full 0 to 10 volts instead of this +4 on the top and -6 on the bottom. So this diode circuit with a capacitor can do that. Then there's another circuit at the bottom. It's called a voltage doubler, which I'm sure you know what that means. You double the voltage. So if you look at this drawing, you'll notice that the output voltage is actually 2 times Vp, where Vp is the peak voltage of the sinusoid. So Vp goes to 2 Vp. I apologize. Actually, it only seems to go to the negative of the input voltage, but nevertheless, the output is twice of the input, and so it needs 2 diodes and 2 capacitors to make this happen. We are not going to study this in any detail, but it's another example of what diodes are able to create. So they help with shifting AC waveforms here and there, clipping, doubling, and so on. Okay. We will look at briefly at a circuit, a real limiter circuit, and how I'm able to chop off just one part of the AC input waveform while leaving the bottom unchanged. And so here's an example of how to do it. You need this battery in line with the diode, and you get this output waveform. You can look at it and understand it. Same thing, this is from our textbook. So with a 5 volts and a 0.7 DC 0.7 volts diode, you can create this where the top is limited to 5.7. So we'll do a problem on this and you'll understand this a little better, but this is an example of a limiter. So the problem we'll do when we are doing the problem section. Okay, the very last slide. I'm almost out of time. I thought it'd be a 50-minute lecture, so give me a couple minutes here. There are 4 types of diodes that are mentioned in the textbook. You can read this. There's not too much detail and we are not solving any problems here, but I'll just read them off to you. The Schottky barrier diode, or SBD, is one type of diode. The advantage of this is it operates much faster than your regular PN junction diode. Also, it has lower voltage drop, so it operates from like 0.3 to 0.5 instead of our usual 7.6 to 0.8. So it's useful in some applications. The next type of diode is a variable varactor diode or a variable capacitor diode, we talked about how a reverse bias diode shows a capacitance property, the behavior of a capacitor, and the capacitance is actually dependent on the reverse bias voltage, right? So the more the reverse bias voltage, the lower the capacitor, I think was the relationship. So that property can be used, and so diodes are specially made only to exploit that property. So they are not used to do regular diode work, but they are just doing variable voltage or variable capacitance type application, particularly for radio frequency tuning and all that. So that is one type of diode. Photodiodes. A photodiode is a diode that can convert light signals into electrical. So they are used for a lot of sensors where you want to, let's say you want to put a sensor by your door, so somebody comes, immediately you hear an alarm in your house. So those kind of applications have a photodiode, and they behave one way when there is no, when the light is falling on them, and then they behave differently when the light on them is blocked or lowered. So somebody comes, then the light on the diode disappears or it reduces, and then it switches on, it conducts current. So that's a photodiode. And a photodiode is also very important in optoelectronics. In fact, it's an essential part of all of this optoelectronics, photonics, optical communications, everything that you guys at CQUPT are very fond of learning, are looking forward to learning. So all of that telecommunications hardware, it all depends on the photodiode. Lastly, LEDs. I don't have to tell you anything about LEDs. China is a dominant LED manufacturing country. LEDs are everywhere, and again, LED is a diode. So it's different from the photodiode. An LED converts current into light. Photodiode converts light into current, right? And one important factor that I thought I would mention, and then we end this chapter, is that the LED is great compared to regular bulbs. Bulbs are only 5% efficient. All the other energy going into a regular bulb is just wasted as heat, but an LED converts almost 60% of the power into light. So it makes much more efficient lighting possible in the world. Okay, so I'll stop with this and we'll do some problems in the next recording. Okay, bye.